Building a generative AI application on a local machine takes an afternoon. Expose that prototype to a global user base, and the system shatters. Moving from a controlled prototype to production scale exposes three structural vulnerabilities. The AI models drift into unpredictable outputs, the required cloud storage triggers exponential costs, and unmanaged data processing creates severe legal liability. When you rely on simple text prompts, thousands of varied user inputs force the model to guess at missing parameters. This lack of constraint causes the system to hallucinate and the outputs to drift far from the intended design. Concurrently, every successful request generates a high-resolution media file. Without a strict retention strategy, millions of these files accumulate on the back end, transforming a lightweight application into an unsustainable data hoard. As that data pool expands across borders, it inevitably absorbs information from vulnerable populations. Processing this without strict governance violates global privacy laws almost immediately. To survive the transition to scale, the concept of a simple API wrapper must be abandoned. It must be replaced by a rigid three-tier architecture, model orchestration, an automated infrastructure lifecycle, and strict compliance gates. We begin at the base layer, model execution. At an enterprise scale, you can no longer rely on standard fast heuristic models. Production environments require thinking models, such as Gemini 3 Pro. These architectures are designed to parse lengthy, highly specific constraints and map them accurately to the final output. To prevent output drift, the prompt must act as a rigid creative brief. Engineers start by explicitly defining the subject and the surrounding environment, removing all ambiguity for the algorithm. Next, they inject strict technical and output constraints directly into the system instruction. This means mandating variables like a 5600 Kelvin color temperature, specific lighting angles, and exact aspect ratios before the user ever submits a request. A highly constrained prompt is useless if the underlying service connection fails. Engineering teams must continuously monitor and route traffic to active, supported API endpoints to maintain application stability. Cloud providers frequently cycle their models. For example, Google Cloud has announced the deprecation of legacy endpoints like Imagen 3.0 Capability 001. To avoid a total service blackout, developers must proactively divert all traffic to the new Gemini 2.5 Flash image endpoint prior to the June 2026 deadline. Even with current endpoints, this layer has operational limits. Guaranteeing exact, pixel-perfect product detail retention during subject customization remains a known constraint in the current generation of models. By strictly orchestrating these endpoints and injecting rigid parameters into the prompt pipeline, you eliminate costly hallucination loops right at the foundation of the stack. The middle layer is cloud infrastructure. This is where the application pays its data tax for successfully serving millions of user media requests. Every generated image requires storage. Expecting an engineering team to manually track and delete terabytes of dead, unused media is operationally impossible. The solution is Google Cloud Storage Object Lifecycle Management. This system acts as an automated custodian for your entire bucket. Administrators write declarative JSON rules that instruct the server to automatically transition files across different storage tiers, based entirely on the asset's age. Using setStorageClass and matchesStorageClass logic, an asset generated today in standard storage drops automatically into cheaper nearline storage at exactly 30 days. As the file ages out of relevance, the rule pushes it deeper into a cold line tier at 90 days. Finally, at day 365, the rule executes an automated delete action. The server permanently purges the asset without human intervention. This line graph maps the cost per gigabyte of storage over a 365-day timeline, illustrating the massive financial impact of this back-end automation. A baseline cost of 2 cents per gigabyte in standard storage stair-steps down to fractions of a cent as it hits archive rates, before dropping to 0 upon deletion. Declarative infrastructure logic forces an unpredictable exponential AI data footprint to behave as a predictable, flat operational cost. The top layer of the stack sits at the user edge, compliance and data protection. Launching a global generative AI tool instantly exposes your servers to interactions from vulnerable populations, specifically children. Processing data from these users triggers strict legal requirements enforced by COPPA in the United States and the GDPR in Europe. Operators must obtain verifiable parental consent to collect personal information from any user under the baseline age of 13, a threshold that jumps to 16 in several EU member states. Standard user interface checkboxes, where a user simply self-declares their age, fail to meet the legal standard for verifiable consent. This flowchart illustrates how some architectures attempt to use AI biometrics for automated age estimation. Operationally, this introduces a high degree of risk. Biometric algorithms frequently perform poorly on disabled individuals or people of color. Relying on automated estimation can easily trigger a discriminatory lockout, illegally blocking large segments of your target audience. The required engineering protocol to navigate this is conducting a formal Data Protection Impact Assessment, or DPIA, long before deployment. The engineering team must also configure the application so that using user data for AI training is strictly set to off by default, legally restricting third-party service providers from scraping your edge traffic. Building these algorithmic and legal compliance gates into the architecture shields the underlying engineering stack from class action liability. When these 3 layers are assembled, we can watch the system securely process a single user request. The payload first hits the compliance layer. Age verification mechanisms and the rules established by the DPIA validate the data, clearing it for processing. The cleared request moves into the model layer. It triggers a rigidly constrained prompt brief and executes through the actively maintained Gemini 2.5 Flash image endpoint, generating the specific media asset. That newly generated asset is immediately deposited down into the infrastructure layer for delivery back to the user. The moment it hits the bucket, the declarative JSON lifecycle clock attaches to the file and begins its 365-day countdown toward final deletion. Production-grade AI functions as a defensive, self-regulating software system, prioritizing structural integrity over simple model connectivity. The raw processing power dictates what the application can do. The rigor of the infrastructure and compliance